Hi everybody, my name is Lukas. I'm the last thing before the coffee break, so you get an elevator pitch now. And I'm happy to present our work titled Towards a Multi-Domain Semantic Architecture for Graph-Based Orchestration of Decentralized Additive Manufacturing. Okay, there's a slide missing, it's not a problem. The work is part of the AIM2PM project. AIM2PM stands for Additive Manufacturing to Predictive Manufacturing, and we are looking into concrete 3D printing also, but also in use of digital twins for it. So maybe main question that comes also from the title is why do we need semantic orchestration here, and why is it decentralized? And actually, even though that the 3D concrete printing is quite unique as a process, the motivation it's kind of the same as with a lot of other construction processes. So current workflows involve multiple stakeholders. They rely on different software systems that can differ quite a lot. We exchange a lot of information across different organizations. And we have the typical challenges of the limited interoperability of our systems, hidden information dependencies, difficult workflow coordination between those organizations, and we lack traceability of the whole process. So what happens where and why? So these distributed AM, so additive manufacturing workflows, require explicit coordination of systems, information, and execution history. This may become a little bit more clear if we look into more detail what's going on. So on the left side, you see typical kind of modules you have in this process. And for example, you have a geometric design, so kind of the planning. You have material composition, how's the material that we print. We need to generate printing paths. We need to align printing parameters that this works well. We want to simulate because we want to know if that will work out. And we also want to do lifecycle assessment of the whole thing that we generate here. And all of those modules we want to integrate with a graph to actually do optimization and control. Because as you can think, when you think about who does these jobs, the person that does the material composition is pretty likely not the same person that did the initial design of the component, and maybe also not the person or not the organization that does the LCA assessment in the end. So we decided to create an architectural concept that consists of 4 domains. So the first one is the system topology. It's a quite simple one. It only describes which system exists in our system and how are they connected between each other. For this, we use Zaref for systems. The second one is functional interfaces. So this is a typical step that you also have in APIs and a lot of online stuff. It just describes how certain APIs or services work, what they need to be triggered. There's a W3C thing description doing exactly this, super handy. We have the third domain, the information requirements. This is the more tricky one because it can change a lot depending on the process. So here we have the questions like which information do we actually need? How does this information needs to be formed and where is it produced? And the last domain is the provenance and traceability. This is actually with Prof.O quite already solved domain because we already have the semantic tools to describe what happens during execution and why. We just need to have a good semantic model and we need to be precise with this, that we can actually also afterwards do optimization. One example how this could look like. So here D1, this is a system topology. We see we have here a topology optimizer module, concrete mix, and LCA module. They are all subsystems of the overall system. And in this domain, we only map them that they are belonging together and are connected. On the next level, the functional description, this is where it gets more interesting because here we describe what here this optimizer module, how I need to actually activate it, how I can speak with it, and what it outputs, what kind of schema. Coming to the third one, the third domain, the information requirements, which then links the schema to an actual representation of the geometry, for example. Here we model, for example, a reference process, what is typically happening in this optimizer and what is the output looking like it creates. And we can also validate this output, for example, in this step. The last step is the provenance. And here we just need to be super precise that we have an activity and we want to model what came in, what was used for that, when did this happen, why, toggled by whom. This is really important that we can optimize among different iterations. How could this play out? So this is an early result just showing where this can go. So you see here a plate, a concrete slab, not plate, and an optimized slab. And we can, if we follow these domains, we can at one point query data that comes from different modules and therefore create information, for example, for LCA. For example, how much CO2 is emitted for the different optimizations we go, which is information we can also only infer because we have different sources. For example, we need to know the cement CO2 per kilogram and how it refers to the design that was in the end chosen. Another cool thing what you can do with such an architecture, I think we didn't hear that enough at the conference so far, is AI. So here you can see a map of our consortium, actually. And this is an interesting thing because our consortium is decentralized and there are challenges among, like getting data among the participants, but it's the same like in the industry because if you are in an industry consortium, it's not a single company that does all of that. However, if we have the D1 and D2 domains, so the functional descriptions in a good way, we can also use those descriptions with an AI agent because they are precise enough that we can kind of generate tools from the descriptions. And this is one example. We want to deploy ROS nodes over our network to different partners. It's a tedious task normally if you're not in one subnet, so over the air between networks. However, as we did a really good semantic description of our tool, also the tool that creates the ROS nodes, we can ask an agent and it is actually capable of doing this. So this is an example where we thought about streamlining the 3D printing process, but realized that the same method can also be applied to have some of our DevOps work taken away from us. So to conclude, we created a 4-domain semantic architecture, separating, for example, topology interfaces, information, and provenance. We used established semantic standards for this, so we did not really reinvent any ontologies for this, nearly all out there already. And we created prototypes for this. There are some limitations, so currently we are limited to one prototype and a representative AM use case. It's still a significant modeling effort to create a system like this. And the whole topics of governance, trust, security, and large-scale validation is not something we touched so far. Outlook, we want to validate this in larger and a more heterogeneous AM ecosystem. Also, it remains open how we can model and validate the information requirements in a better way. And in the end, we want to use the system to actually come to simulation because that's what the project is about, that we not only print, but also predict how our prints will end up. And that was it for me.